talking about, if we were in signal space, we're talking about one-dimensional signal space, we're talking about sending more than one bit at once. So one-dimensional signal space so what we really want to do is we want to send M-ary information where M is something greater than 2. And my technique for doing this is that I'm going to have some fundamental basis signal. So if I have a one-dimensional signal space, how many basis vectors do I have in one dimension? Well, one, right? So I have one basis signal, and I'm going to call this K. And I have symbols in my alphabet. My alphabet is the set of symbols that I'm willing to send. Now it's not just 0, 1, it's 0, 1, so on, up to m minus 1. I do it this way. I could do it 1, 2, 3 up to m, but I want to be consistent with binary, where I had 0 and 1. So I'll start at 0 and end at m minus 1. What we're going to do is we're going to argue that, or excuse me, we're going to say if I want to send a symbol, I use the modulation function SI. Okay, and that's equal to, okay, if this is a one-dimensional signal space, everything has to be a multiple of the one basis function. So SI of K is going to be equal alpha I times S of K. Now, remember from last time, without loss of generality, we're going to assume that the alpha i's are arranged in decreasing order. So alpha 0 is the biggest, alpha 1, alpha 2, and so on, up to alpha m minus 1. I'm going to insist that they are strict inequalities. I'm not going to let any of them be equal to each other, because if they're equal to each other, then they're the same signal. So there's no benefit to that. So today what we're going to do is we're going to talk about error analysis. We're going to try to see if we can write down, so you remember when we talked about baseband transmission, we wrote down an expression, a general expression for the probability of error, and then we optimized it. So what we're going to do here is we're going to do the same thing. And we're going to kind of follow the same roadmap. So we started talking a bit about this last time, but I'd just like to go back over it. So our general recipe, our general procedure for probability of error in binary, we did 3 things. Well, step 0 is we gather all the information. So given signals, thresholds, and the filter, what we do first is we find the noise-free filter outputs. Second thing we do is we find the variance. The third thing we do is calculate probability of error. Basically by substituting them into a big equation that I'm going to derive. So, what are my noise-free filter outputs? So this is all reviewed. This is exactly what we did in before the break, before the midterm. So once again, we see that all these same concepts come up. So basically, there's not a lot new to learn here. It's just things are going to get rearranged a lot. Pick up your midterm. Right. So, one thing that I said last time was that it's nice to deal with orthonormal bases. An orthogonal basis is kind of meaningless in one dimension, but I do want to deal with normal. So I'm going to say my basis vector S of k has norm S of k equal to 1. So, my noise-free filter outputs. Si, if signal I is sent, then waveform Si of k is sent, and the IF noise-free filter output Si, which is Si of k involved with h of k, evaluated as NB. I can substitute in for this with alpha I S of k involved with h of k. And B, then I can take out the alpha I. Like so. And this will finally be alpha I times this expression I called H. So as long as H is 0, okay. As long as H is positive, I'm okay, non-zero. So what's going to happen is that since, I mentioned this last time as well, alpha 0 greater than alpha 1, greater than alpha 2, greater than so on, greater than alpha m minus 1, and assuming H is greater than 0, which it should be. If I've designed my filter correctly, it should be greater than 0 because I should be getting something that's positive out of here. In other words, if I send my signal in on my detection filter, I apply my detection filter, that it should be positive. Then it's clear that S0 is greater than S1, greater than S2, and so on up to S m minus 1. So this is basically where we got to last time. Here's my number line, my real number line. So this is just a depiction of a one-dimensional space. It's just a line, right? So I can have my signals S0, S1, S2, and so on up to Sm minus 1 as points along this line. Okay, the noise variance, that's the second thing we have to do. The variance, sigma squared, is N0 over 2Ts, this is the formula from the notes, N0 over 2Ts times the sum of the filter coefficients squared. So if that's true,